So today's all about graphs of logs, and then we'll also kind of tie in the domains of logs. Uh, but how we're going to graph a log, because right, it's still a weird thing, and I've had the question of why is log? What is log? Why does it show up in the equations? And again, it's just the inverse of an exponential. The weird part about it is it seems like a word, and why do we have words in these equations? So, and I understand why we tend to get confusion with this whole unit. So what we're going to do to graph a log is we're going to use the fact that a log function is the inverse of an exponential function. So we're going to start with the corresponding exponential. After we correspond with the exponential, we're going to essentially switch the x and y. That's one thing we've done with inverses already. And that's going to ultimately get us our points for our log function. And then just like what we did with graphing exponentials, if there are any transformations, we can apply them to the parent function, shift them left, right, up, down, whatever those transformations might end up being. All right, so in this first example, we're really trying to graph log base 2 of x. Now, before we do this, and this kind of tells us where to start, you're going to actually think about what is the base of the log that is going to be the base of the exponential, and we're going to start with that. So we're going to start by actually graphing f of x equals 2 to the power of x. So I'm going to have an x value, and we're going to come up with y, 2 to the power of x. And let's plug in -2, -1, 0, 1, and 2, giving me y values of 1/4, 1/2, 1, 2, and 4. So these are values for the inverse of log base 2 of x. And so we're ultimately working on being able to graph this log function. And so we're going to make another table of values of x, and then the y values here come from log base 2 of x. Well, knowing that 2 to the power of x, log base 2 of x, are inverses of one another, we can graph these by taking the domain, making it the range, so x's become y's, and the range becomes the domain, so y's become x's. And so we don't even have to think about evaluating any logs here. We can just copy over the y's for x's and the x's for y's. Okay, and then we can go ahead and graph those both. In this case, we will graph both of them on the same graph. Maybe for the next one, we'll just graph the log function. So I'll go ahead and do this in red, the exponential, and then the log in blue. So exponential, we know that we have horizontal asymptote. And I have -2, 1/4, -1, 1/2, 0, 1, 1, 2, and 2, 4. Three, 8 would be another point. I'll just add that in there just to allow this to span the whole graph. And so then for our inverse, so the log function, really what we're working on graphing here, when x is 1/4, so just to the right, y is -2. When x is 1/2, y is -1. When x is 1, y is 0. When x is 2, y is 1. And then 4, 2. So what happens in a log function is it has similar properties. Instead of us having a horizontal asymptote, like we do with exponentials, we actually end up getting a vertical asymptote. And that's going to come from the domain. Okay, and one thing that we did chat about with inverses, we didn't do a whole lot with this, but I did mention to us that inverses, we can tell a graph is an inverse of one another if it is reflected across the line y equals x. So in green, just so that we can see this, I'm going to go ahead and graph that line y equals x. And so if we were to reflect these graphs across this line, they're going to be symmetrical, right? And we can kind of see that here. If I take this red one, flip it over that line, we get the blue one. Okay, all graphs that are inverses reflect across that line y equals x, which is why when we take the composition of inverse functions, they always work out to be just simply x. Okay, so most of this is extra for what we're really working towards. Okay, and here in a second, I'll talk about just the basic things for what we need to know moving forward. So I want us to think about the domain and range of logs. Well, if we know the domain and range of exponentials, they essentially switch. So when I think about the domain of my exponential, it is negative infinity to positive infinity. Well, that domain of the exponential is going to become the range of our log function. So the range for the log, in this case, is negative to positive infinity. Okay, and we see that in the graph. It's going to go all the way down to negative infinity. It's going to go all the way up to positive infinity. In other words, when we start plugging in values for x, we're going to get both negative numbers, we're going to get 0 and positive numbers. In a log, it's the domain that's going to be restricted. And again, we can tie that back to an exponential. When we think about the range of 2 to the power of x, the smallest we can get 2 to the power of x to be is basically 0, right? We get really close to 0, but not all the way there. We're seeing that in this horizontal asymptote. And so knowing that the range of an exponential is 0 to infinity, that's then going to become the domain for our log. So the domain for the log is 0 to infinity. And we're seeing that from this vertical asymptote here. The vertical asymptote, we will never touch a vertical asymptote. We will never cross it. In this case, everything is going to always be to the right of that. So how can we pay attention to this moving forward? Essentially, you cannot take the log of 0 or negative numbers. And that's a really important property of logs. And it all stems from the values we can obtain in an exponential, right? When I think about 2 to the power of x, I will never get this to be 0. Okay, that's in the range of the exponential. And I will never get 2 to the power of x to equal 0. That translates over to the domain of our log. So just another reminder, when we're thinking about logs, it's helpful to think about them in terms of exponentials because we're a little more familiar there. Yeah, Blythe, what you got? That's just y equals x. That's the slope is 1. That's just the parent function of a linear equation. We don't need to do anything with this line. That's just me kind of reminding us that on the graph of a function and its inverse, it'll always be reflected across the line of y equals x. Yes, yeah. More of a thing to kind of remember for other things we're doing with inverses. We don't need to worry about that for here. Okay, so in this next example, let's talk about what do we really need to focus on to be able to graph logs. And then also describe the domains and the range. And sorry, before we do that, equation of the vertical asymptote, it's going to come from the horizontal shift, knowing that we can't take the logs of 0 and or negatives. So in this case, it is x equals 0 for the equation of that vertical asymptote. Okay, we will never get to 0 and we'll never be left of that equation of x equals 0. Okay, so in this case, let's change this problem up. Let's just work on graphing g of x. Let's not even worry about f of x. Let's just put the whole log function in the equation. So how do we go about doing this? We're going to start with the corresponding inverse, which is the base itself to the power of x. So we're going to start with values of x and then 1/2 to the power of x. And again, -2, -1, 0, 1, and 2 are always good x values to use. So 1/2 to the -2, that flips the base, making this 2 squared, which is 4. 1/2 to the power of -1 flips the base, so it's 2 to the power of 1, which is 2. Anything to the power of 0 is 1. 1/2 to the power of 1 is 1/2. 1/2 squared is 1/4. Now, the only reason that we came up with this table here is to then use those values to come up with values for our corresponding log. So we're still going to have x values. This time, our y values are represented by log base 1/2 of x. And so the domain of the exponential, or the x values, become the range of the y values. And then the range of the exponential, or the y values, become the domain of the log, or the x values. So we just switch these two columns. So this is 4, 2, 1, 1/2, 1/4. And then the x's that become the y's are -2, -1, 0, 1, and 2. Okay. So I can go ahead and fill in that vertical asymptote right from the start. Again, it's whatever value is going to make us take the log of 0. So in this case, if x is 0, that's a problem. That's an error in our domain. Okay, they really are domain restrictions. So we still have that same vertical asymptote at x equals 0. We'll come back to the domain and range from there. Let's just go ahead and plot these points. So when x is 4, y is -2. When x is 2, y is -1. 1, 0 shows up on just about every graph. And then when x is 1/2, y is 1, 1/4, 2. Okay, so we would expect this to be a little bit different since that base is a fraction. Right when it's an exponential, that's a decreasing exponential. We wouldn't describe this as increasing or decreasing. I guess technically it is decreasing still. Yeah, it's still decreasing. And any questions up to this point? Kind of saying how we can use the exponential to get the log. I feel like it takes a lot of the thinking out of what the log is, which makes it a little more straightforward. Okay, so our domain, and again, this is of the log. Remember, we can't take log. The number that's going to work for our domain is just past 0. So 0.0000, however many zeros you want to say, and then a 1. And then it's going to go to positive infinity. Since the domain of an exponential is always negative to positive infinity, that is the range of our log. Negative infinity to positive infinity. And that'll be true for every single log. Bless you. So when we're graphing a log that has multiple transformations to it, naming the transformations can sometimes help. Why don't we start with that? This 3, that's our vertical stretch. This 2 shifts everything left 2. And this 5 shifts everything down 5. And so we're going to apply all of those transformations to the parent function. The parent function here is the most basic of this log equation. So the base will stay the same, and then it's just of x. So the parent function, I'm going to use y as y equals log base 2 of x. So we're still going to graph this. After graphing this, we will then go ahead and apply all these transformations to that graph. Now, in order to graph this, we're going to start with x values and y values for its inverse, which is the base to the power of x, so with the exponential. -2 to +2 will always be values we start with. And I get 1/4, 1/2, 1, 2, and 4. So then, for our log, we have x, then log base 2 of x. And I'm going to take all these x's and make them the y's. So domain becomes the range. It's -2, -1, 0, 1, and 2. And all of the y's, so our range, become the domain. So 1/4, 1/2, 1, 2, and 4. So I'm going to plot all those points. I am going to wait to draw the vertical asymptote though, just it'll get a little congested with that. I'm going to apply the vertical asymptote at the very end of this. So we're just going to plot these points and apply this transformation. So when x is 1/4, y is -2. X is 1/2, y is -1, 1, 0, 2, 1, and 4, 2. Okay. So, and I'll use different colors here. Right now in blue, this is log base 2 of x. And then since we have a vertical stretch in here and horizontal and vertical shifts, we have to do this in 2 different steps to apply these transformations. And this is one thing we covered when graphing exponentials. We have to start by applying the vertical stretch. So we're going to actually do 3 log base 2 of x. When we have a vertical stretch, remember when we talked about transformations, we can always think about what variable is affecting. X is not changing, right? This x from our parent function to this x in the function that has the vertical stretch doesn't change at all. What's going to change is after we take the log of that x, it's then going to get multiplied by 3, essentially telling us to multiply y by 3. And that's how it's going to stretch it out. So I'm going to take all these y values and multiply them by 3. So 2 times 3 makes that 6. 1 times 3 makes that 3. 0 times 3 is still 0. -1 times 3 is -3. -2 times 3 is -6. So the asymptote has what we've done is stretch that graph out. And we can see that, right? That's a really good representation of it being stretched out in both directions too, right? Towards the bottom of the page and the top of the page. And then after applying the vertical stretch, now we can go ahead and apply all the horizontal and vertical shifts. So the last thing we're going to do is graph 3 log base 2 of x plus 2 and minus 5. And so basically, I'm going to take each point, shift it left 2 and down 5, and that'll come up with the function we're trying to graph. So this one here at -6, that x is at what? 1/4. So I'm going to go left 1, 2, and then down 1, 2, 3, 4, 5, slightly off the graph, but all good. Next point, left 1, 2, down 1, 2, 3, 4, 5. This point at 0, 1, left 2, down 1, 2, 3, 4, 5. Left 2, down 1, 2, 3, 4, 5. And left 2, down 1, 2, 3, 4, 5. And so it does get kind of congested with 3 different graphs all in one. That's why the colors help. That's it. So the only thing that we have not done and have not added in here is the vertical asymptote. That vertical asymptote essentially comes from the horizontal shift, right? And a couple reasons for that, right? That vertical asymptote is originally at x equals 0. And so we're shifting it left 2 to put it at -2. Okay. Another reason we can see this in the equation is if I plug in -2 in for x, now I'm taking the log of 0, which is a problem. Okay, so that's one thing we are going to kind of separate from the graph, work on describing the domain, which we'll do towards the end of these notes. Okay, any questions here on how I'm coming up with these values or applying any of these transformations? All right. Well, let's just real quickly describe the domain of our function. Remember, we can't take logs of 0 or negatives. So the smallest value that works here is just past -2, and it goes to infinity. The range of every log is -infinity to +infinity. And then the asymptote here is for whatever value makes us take the log of 0, which is -2. So x cannot equal -2. Okay, we're going to do one more example. I'm going to actually get you all to kind of work through this and apply all the transformations on your own or in your groups. And the reason I want to do one more is just to remind us about the different types of logs. So natural logs, we covered this a couple different times, so this is more of a reminder that a natural log is a log function with the base e, and it is called the natural log function. So if you ever see log base e, it is the same thing as just ln of x. You're typically going to see it as ln of x. Now, you can always rewrite it. You can take anything that has this ln or natural log and simply write it with a log that has a base. So we could think about this as negative log base e of x plus 3 plus 2. You don't need to do that, but by doing that, I can clearly see what the base is, and it gives me some idea of how to start to graph this function. So I'm just going to go ahead and get us the values for our starting exponential, and then let you kind of take it from there, and then we'll check it after you've had some time to work on it. So we're going to go ahead and let's write down that parent function. Bless you. Which is just natural log of x, which is really log base e of x. So we're going to start with the same x values from -2 to 2. This time the y values come from e to the power of x. And so we need to know how to find e on the calculator. It's going to be the inverse or second option of the ln button. So all your calculators should have this ln button. And so I'm going to go second ln, and if you see it above that, that's e, and allow me to take the powers or any exponent. So we'll start with -2, and let's just do like 3 decimal places, so that'd be 0.135, and then -1, 0.368. Anything in the power of 0 is still 1, and then e itself is 2.78718, and then e squared 7.389. So we have a ton of decimals, making it a little bit more challenging, but the process is essentially the same. So take it from here. Okay, either in your groups or on your own, work on translating this into the natural log of x. Graph that, then go ahead and apply the transformations to that function. See what you come up with. Give it a few minutes to do this. We'll go over it and then just recap about domain of logs to close this out. All right, you're all set.